screen mode. So see, this is a question of insanity being when you do something the same way every time and expect it to come out differently. But I have defeated that demon because I'm not going to do it, right? I'm not going to repeat it again. Okay, so first of all, we have ourselves the emitter follower. And okay, I'm jumping past the very beginning. So he does say in there, normally you put a base resistor, but you don't want it to be any more than 1K. And there's a couple of reasons why. But the most important reason, you can figure it out because you know that IB is on the order of microamps. So if you make this base resistor too large, number one, you're affecting uh, the output impedance of the source because it becomes an R-Thevenin all by itself. But the also is that what happens when a current flows through a resistor, right? So you're looking for compliance, meaning that you have a V in, say at A here, or a V from the V Thevenin. You want VAB as close to 0 as you possibly can. So I've pretty much given away uh, the farm there, but I want you to think about it. And another thing we notice about emitter followers, and I realize I could have done, I've shown you that the gain of a transistor in this configuration, well, not this strictly, the gain is equal to R collector over R emitter. Now we don't have an R collector at the moment, but there's a way to calculate the gain. And you may have noticed that the gain of the emitter follower, and it said capital G of an emitter follower is about 0.9 or so. So you're wondering to yourself, well, what's the good of it? And it's in a very important, it's one of the very first circuits I learned after working with some pretty high-end electronics, but not really knowing exactly what I was doing. And my first real job when I got my master's degree, my boss taught me about the emitter follower. It was a great way. We got potential devices to test that were made to measure very tiny signals, and they had very tiny outputs. So he just said, whenever you get something like this, you just slap an emitter follower after it. And now we're going to learn why. So the key is, at the end of the day, the Z in and the Z out. So we want to measure the Z in of an emitter follower, and congruent with this idea that our base is not supposed to be too large, that's basically, in this circuit, point B. So in this case now, we have an R base that's much greater than 1K, so we're violating our rule of thumb, because what we're going to do is we're going to say that RB is a stand-in. I couldn't think of the right word. Is a stand-in, like a double, a stunt double, for Z out of the source. Because we know that our function generators have a ridiculous, they have a very low Z out. They have a 50 ohm Z out, so they basically can supply all the current that we need to maintain a certain voltage. So first of all, we need to, let me think about this. So we need to back up a little bit. First thing we're going to do is measure our V out in this configuration. And already you can see, you can kind of get a hint like, well, why don't we put a 270 here? Why is V out with a 33K important? And that's because ultimately what we're going to see that this thing does. But the first thing we're going to do, maybe that's on the next slide and I'm jumping the gun. No. Never mind. And so the first thing we're going to do is now, oh, I'm sorry. I know what I'm doing wrong. That's the Z out. We're doing Z in now. I added this in the last minute, so I'm confusing myself. So anyways, we're going to look at the voltage across this resistor, VA and VB. And so we're making a voltage divider of the RB and the Zin of the emitter follower. So that means that the voltage we measure at A is the stand-in for V in, and the voltage we measure at B is the stand-in for V out. Because remember, we said that the Z in is at point B. If we had a very small resistor here, then A and B would both be good enough for V in. Okay. And then we have our voltage divider. We have our standard voltage divider equation for a two-element voltage divider. And since Zn is in the R2 position, that's up here on the numerator. Seen it over and over again, right? Okay, so I'm going to go forward if that's okay. Okay, so you see now I just brought forward the two circuits. I brought forward the equation. So what we do is we do what's called an ansatz, and we just guess at the answer. And we say to ourselves, okay, what would happen if V out over V in equals 1/2 exactly? So you do out the algebra, do a cross multiplication, then do the distribution, distribute the 1/2, do the algebra, gather your variables, multiply by 2, and you end up with that Zn equals the R base. So if we adjust R base until we get a V out over Vn equal to 1/2, we find out what Zn is. And in this case, they expect you to get about 330K in this setup. And it doesn't matter what the volts are. The VCC and the VEE don't matter about Z in or Z out. Z in or, oops. Of course, that's going to be hard to do. And of course, that's going to have some, look at the latency. Draw, erase, Z in or Z out. Okay. All right. And it actually doesn't matter what 3.3K is either. Well, okay, it does, but sorry about that. It does matter. Basically, when we look at this thing, a voltage divider, and now in this case, RB and RE we would claim that the input impedance is the 270 plus the 3300, which is basically 3300. But the transistor makes it look like 330K in this case. And so the implication is that Zin is equal to beta times R base. Because remember, R base determines the current. You have a voltage drop, you have the small voltage drop from V base emitter about 0.6 volts. And this is why the output, the gain of the emitter follower is about 0.9. But other than that, whatever the voltage is at the emitter, and then R emitter determines what I is through the transistor. But what it also does is it means that we get an apparent Zn of 3300, but our real Zn is 100 times that. And if you have a so-called high impedance source, now what's a high impedance source? Okay, a high impedance source would be if I have two metal plates, two conducting plates, and here I have an amplifier attached, and which would be my emitter follower. Here I have negative 5,000 volts, and this end is at ground. Well, it's at ground through it's at 0 volts. It's not at ground, but it's a 5,000 volt potential difference. Then I put this thing, and I have inside here, let's say one thing I work with, I have liquid argon in here. So we have then a high energy electron or high energy proton comes zipping through, and it ionizes the argon and leaves a whole bunch of electrons in its wake. And let's say we have, say, a microcoulomb of charge. And because of the high voltage, they march across to the right. And in principle, they can induce a tiny signal. Typically, in one of these things, the time that it takes for them to drift across is 400 nanoseconds. And you figure out that the current is very low. And you can get and if you have a very high impedance input, you can get a nice voltage. If you have and so the output impedance of this is really, really high. So it can't drive anything. So I have to have an extremely high input impedance. In fact, this thing is set up that it has a 1 megaohm input impedance. And in fact, it's not done with an emitter follower. It's done with an op amp, which we're going to study soon. And it's a special configuration that makes an input impedance of mega ohms, because you only have a few million electrons available there to drive a voltage, make say 1 volt, and let you. And if you try to drive a couple hundred ohms, it's never going to happen. So this is similar to the analog voltmeter weighing down a circuit, right? So you want any amplifier to have a very high input impedance. That's your goal. And that's what a transistor does. Before transistors, you use vacuum tubes, and that's a good question. I don't think that they could achieve a 1 mega ohm input impedance. I have to, because of course, they weren't used for this kind of signal. This is work I did on my master's thesis, but there's other examples. Okay, the next step is that we want to measure now the Z out. This one is the one that's a bit harder. So first of all, we measure V out, unloaded V out. Typical, this is a standard decomposition. The unloaded V out, which is going to be a peak to peak, that's easiest, right? This is going to become our V Thevenin. Now, I don't know if you guys tried it by measuring the voltage here or not. For some reason, he says it's not possible, but if you can measure V in at this point, fine. But as long as you know what the V out is here, unloaded, then you can do this, at least because he's chosen the components for you. So just as, again, we form a voltage divider, when we add a load resistor, we form a voltage divider with the output impedance of our source, which is in this case, the emitter follower. We can ignore the output impedance of the function generator because it's only 50 ohms. And we already know that the input impedance at 330K means that there's no way in the world we have to worry about the impedance of the function generator itself. So now we know that the standard voltage divider equation. And just to make our lives easier, so we don't have to write V out over V in over and over again, we're just going to call it little letter A. And so then we do our cross multiplication as before, because remember we had A over here on the left. So we bring the denominator up here, we distribute A, gather our terms, and then we're left with this expression for Z out. Now, of course, they want more than that, because he tells us that we can infer beta. So this is the fairly easy part, and also the fairly easy part to understand. But we're still going to go back to our old friend, the voltage divider. Is it okay to move forward, or is anybody please, if you want me to go back, make sure you tell me. I'll go back to the one before this. Okay, I'm going to move forward. So now what we do is we kind of think of, there's the transistor is maybe, I said black box, but maybe that's, well, yeah, we can assume that the transistor is kind of a black box. And we're going to assume that it must be a kind of a voltage divider. So it has some, and we see RE, but we don't know much about RB. We know we have to assume there's a resistor back there. So if we use that model, and I guess we know there's an RB there. We just don't know quite exactly what the transistor does. We can calculate a Z out of this voltage divider. We've done it many times. And it's just adding RB in parallel with RE. And so that's RB, RE over RE plus RB, right? It's nothing new here. Even this particular equation in specifically, we've already seen. And then once again, we do our algebra, same exact algebra, and we get an expression for RB. Because at the moment, we're assuming we don't know what it is. Okay. So we look at everything, and I measured a Z out of about 0.3K, maybe 0.33K. And I know that my RE is equal to 3.3K. And I explicitly chose an RL equal to 1.0K. And let's be careful. What did I do here? I said that I didn't. Did I calculate? Oh, yeah. Okay. That's right. This is Z out, not. Okay. Let's go ahead. Sir? Let's go back. Welcome. Ready? Okay. So I measured an A of 0.77. And so that told me that my Z out of the emitter follower was 0.3K. So if I plug that into the voltage divider equation for the Z out, for the voltage divider equation for RB and RE that we see up here, that tells me that RB should be equal to 0.33K. But we know that it's actually 33K. So remember that R base is masquerading as the output impedance of our source. And that tells us that the emitter follower takes whatever Z out and divides it by 100 in this case, which is also our beta. So basically, an emitter follower takes a weak source and turns it into a so-called stiff source. So you could have a high impedance source, and the emitter follower turns it into a low impedance source. And that's the point, because yes, we don't get any voltage amplification, but we get major league current amplification. And at the end of the day, what you're delivering is power. And so, and also, we have wiggles going on. We're not quite so interested in the amplitude of the wiggles as it is the behavior of the wiggles. And we can always calibrate back, right? If we know the gain of our emitter follower, we can always take the output in volts and calculate what it is at the source. So you always have to remember that even though our signals we speak of are described in terms of amplitudes and volts, that you have to have a certain amount of current ability to make that voltage happen depending upon the load. And the load it matters because we need to know what is the Thevenin resistance or the Z out of a source. And the emitter follower is basically an impedance changer. So it's amplifying, but it's doing it in a hidden way. It's a very powerful little thing. It has long since been superseded by op amps, but it shows you what transistors are doing under the hood, so to speak. Because everything, even the display on your laptop, the little pixels are transistors. They're actually switches, but they're still transistors. Okay, what's next? All right, so let's make sure everybody's got this. Then I'm going to just fill in a few little pointers, and then I'll talk about the common emitter amp. No, what comes after this is the current source, excuse me. Then the common emitter. Okay, so let's see here. They said to us, we're going to add a cap. He also said maybe the cap isn't such a big deal. So basically, and this is an example of a blocking cap. There's blocking caps and bypass caps. And that has to do with their usage, not with what they're made of. So remember, the resistance of an ideal capacitor is infinity at DC. So you can't, capacitors in series block DC. And in this case, if there was the ability for a DC flow, notice that with 1K and 3.3K, the effective base resistance can change significantly. You would then change I current, IC, the current in the emitter, the collector, and the emitter, and you would change the gain of the emitter follower. In this case, it's not a big effect because the load resistor is 1/3 of the base resistor. I mean, emitter resistor. And the way you pick it is that you have a time constant, in this case 4.7 milliseconds. If you invert that, that might be 120 hertz or maybe 180 hertz. So as long as you have a frequency above that, the capacitor has no effect on the output signal. But it blocks any current from bleeding off through the 1K resistor from the emitter voltage point down into ground, which would affect the voltage of the emitter and would affect the gain of this device. So that's the reason there's a capacitor. Now, as stated before, you don't normally use such a large base resistor. We just use it to masquerade as the Z out of the source. Basically, when we're playing with the emitter follower all by itself, we put in a 270 ohm resistor. And what happens is when you send a signal down a line, and even if it was DC, it would be the leading square edge. They have a tendency to reflect off connectors. So it leaves the function generator, it comes to the base of the transistor, which we know has a really high input impedance. And if it has a high input impedance, you have more of a chance of a reflection. So you're bringing a sine wave in, the sine wave comes back, and then it re-reflects back into the base. And if it does that, you get what's called its feedback, just like when you put a microphone too close to a speaker, and it whistles, it goes into oscillations. I forget why it goes to high frequencies. It must be a beat frequency because you don't have any guarantee that the sine waves are in phase. So if I put in that resistor of 270 ohms, in the case of one reflection, the re-reflection, by that time it's passing through the 270 ohm resistor for the second time, and each time it gets its amplitude knocked down because there's a voltage drop across the 270 ohm resistor, and that tends to kill the oscillations. And don't forget, I'll post this. And maybe this is 30 minutes of video. I'll stop this and start a new one.